Hi, chemistry students. I want to touch base with you quickly here about the law of conservation of mass. So this is a pretty small section in the reading that we've done, but it's a pretty big concept in chemistry overall. And what it basically says is that in physical and chemical reactions, mass is conserved. So as long as the change that you're looking at or the change that you are investigating is physical or chemical, you're not going to create mass, and you're also not going to destroy mass. So that's true for almost everything we deal with in our class this year. Almost everything we deal with in our class is going to be physical or chemical change. And so in all of these scenarios, our mass isn't going to increase between what we start with and what we end with, and our mass isn't going to decrease between what we start with and what we end with. You can see it's said a little bit differently down here. During any chemical reaction, also true for physical changes, the mass of the products is always equal to the mass of the reactants. So we see two words here that I want to make sure that we understand: products and reactants. So reactants are the things you start with in an equation. They're your starting material. They're there in the beginning of the experiment, and then they get pulled apart and mixed around and used up. And in the end of the experiment, we don't have the reactants anymore. We have something different called products. Products are present in the end. They are the material or the substance that we end with. So you can see down here in our little example, we have a chemical reaction right here. This arrow in the middle is what indicates our change. That on one side of the reaction is what we start with. These are called the reactants. And on the other side of the arrow is what we end with. And these are called the products. Okay, so we start this experiment with hydrogen and oxygen gas. So in the beginning, we collect hydrogen and oxygen gas, and we put them in a container. And then in this scenario, we add a spark or a flame of some sort. And the oxygen and the hydrogen are actually going to get pulled apart. They're going to pull each other apart and get rearranged. And in the end, we don't have oxygen and hydrogen anymore. Not oxygen and hydrogen gas, at least. The oxygen has been pulled apart and rebonded with the hydrogen. The hydrogen has been pulled apart and rebonded with the oxygen. And what we have now is we have water. We have a new substance with a totally different set of properties. We have water. So water is our product. Water is present in the end. Hydrogen and oxygen have been used up and are no longer present. So if we look at this example, and we look at the actual molecules in this sample, we can see the law of conservation of mass here. Notice in the beginning of our reaction, we start with 1, 2, 3, 4 hydrogens. In the end of our reaction, we start with 1, 2, 3, 4 hydrogens. We haven't created any new atoms. We haven't destroyed any hydrogen atoms. They've just been rearranged. Similarly, if we look at the oxygen, in the beginning we start with 1, 2 oxygen atoms. In the end, we end with 1, 2 oxygen atoms. We haven't created any oxygen atoms. We haven't destroyed any oxygen atoms. They've just been rearranged. And this is the law of conservation of mass. We looked at this in this picture in terms of atoms. You can also look at this in terms of mass. So hydrogen weighs about 1. Let's round it off to 1 for now. So in the beginning of this experiment, we have 4 grams, 4 AMUs of hydrogen. In the end, we're still going to have those same 4 AMUs of hydrogen, exact same amount of mass. That mass has just been redistributed in new ways. In the same way, oxygen weighs about 16 AMUs. So in the beginning, we have 32 AMUs of oxygen, and in the end, you can see we still have that same 16 or 32 AMUs of oxygen. We haven't created any mass. We haven't destroyed any mass. Initially, what do we start with in terms of mass? So 32 plus 4 would be 36 grams. And then in the end, we still have 2 times 16, which is, oh no, I added that wrong. 2 times 16 plus 4, 36 grams. There we go. Our mass is consistent. We don't create mass. We don't destroy mass. We just rearrange it. And that rearranging of those chemical bonds is what results in new properties. It's not the addition of mass or the loss of mass. It's a rearranging of bonds, of chemical bonds, ending up with a new molecule or a new arrangement of chemical bonds we didn't have before that results in brand new properties. Okay, so law of conservation of mass. That is what the gist of it is conceptually. Now let's look at it mathematically. Okay, so in this example, this would be a really great time to pause this video and just read this example for yourself. It's talking about when ammonium nitrate explodes. The products are nitrogen, oxygen, and water. So we can actually write this out in terms of words, or we can write this out in terms of pictures. I'm going to write it out in words first. So my reactant, my only reactant is ammonium nitrate. That's the thing I start with in the beginning. In the end, I have 3 products. I have nitrogen, I have oxygen, and I have water. Okay, now 40 grams of ammonium nitrate explodes, 14 grams of nitrogen, and 8 grams of oxygen form. How many grams of water form? Okay, so I can assign these amounts to my reactants or my products. So 40 grams of ammonium nitrate. And that side, that reactant side, should equal my product side. So my product side includes 14 grams of nitrogen, 8 grams of oxygen, and some amount of water. I'm just going to put an X there for now. So again, I've set up my equation to represent the law of conservation of mass. The reactants should be equal to the product. I have the mass of the reactants equals the sum of all the mass of the products. And then I just solve for X. So 14 and 8 together is going to be 22. So I'm just going to subtract 22 from both sides. I want to get that X by itself. So now X is by itself on one side of the equation. And I have 18 grams on the other side of the equation. So 18 grams of water must have been formed. This is how you would approach a problem like this that deals with the law of conservation of mass in numbers. Okay, just one more thing conceptually I want to deal with before I let you go here is something that you've had a chemical change that you've had a lot of experience with. And when we were talking about physical and chemical changes, almost every chemical change that we referenced was burning. So what about burning? If you take, let's just think of a piece of wood, for example, okay? So you're going to take a piece of wood. Here you go. Here's my nice piece of wood. Oh, that was not a great drawing. Wait for it. I can do better than that. Okay, there's my piece of wood. It's so cute. Okay, all right, we're going to sit around a campfire and we're going to enjoy the lovely heat that comes off of our campfire. So we light our wood on fire here and we let it burn and we look at the stars and we feel the warmth on our legs, maybe a little too much warmth, so you have to rotate a couple times. Okay, so we have this log in the beginning. We add some heat, our log burns, and in the end, we just have a couple pieces of ash left over. Okay, so have we conserved mass? It's definitely a chemical reaction, right? We said so over and over and over again on those chemical and physical reaction problems, right? But I don't see the same mass. We definitely don't have the same mass of our log in the end that we did before, right? Our ash is light. The ash is super light. It blows away. It's so light. So where did the mass go? Now would be a good time to pause this and think about it for 30 seconds and see if you can come up with an answer. And the answer is, anytime you burn something, you always produce two things. So this is why chemical reactions can be a little bit deceptive. So when we burn something like wood is going to be a hydrocarbon. So we're going to have a certain amount of carbons and a certain amount of hydrogens. It actually gains mass from the atmosphere because the oxygen in the atmosphere is part of our reaction. And then whatever results is probably going to be carbon. That's the ash that's left over. You're probably going to have an incomplete burn. So you're probably going to produce some carbon monoxide. But the two things that are always, always, always produced in a combustion reaction where you burn something are going to be water and carbon dioxide. And here's where the bulk of your mass goes. Yeah, some of it's left over in terms of carbon in the ash that's sitting in your fireplace, right? But the bulk of your mass is going to be gas, gaseous water and gaseous carbon dioxide that gets released into the atmosphere. And so it's hard for us to see that conservation of mass if we're just releasing the gases in an open container. We're not closing off this container and collecting all the gases in the end. If you were to do that, you would see that everything you start with is still there in the end. So for chemical reactions, we'll think about this as we go through more examples, but conservation, the mass is always conserved. We're not creating mass, we're not destroying mass. Sometimes it's hard to see where the mass ends up going, but it is always there. All we're doing is rearranging atoms and forming new chemical bonds, but we are not creating or destroying mass. Okay, good job. Let me know if you have questions. I'll see you in class.